Hello everyone, this is Siddharth SIngh Parihar. I am going to teach you VLSI design. Today's topic is structure, digital circuit and system. In this topic, we include random and structural logic forms, register storage circuit and microcoded controllers. This topic belongs to lesson plan number 18. Let's start. Before we go for structure, digital circuit and system, we have to know some terminology, that is regularity. Okay, so in VLSI design, regularity means simply called hierarchical decompositions, okay, of a large system. And in hierarchical decomposition, we reduce, or we can say that if we have a similar blocks in our circuit design, then we considered it a single block. Okay, this is called a hierarchical decomposition. If we take an example, then in our design, if in our design array structure consisting of some identical cell. Okay, if we take example like a parallel multiplication array, then we have a identical cell. Okay, so in other words, we can say that we can use resource reuse. Okay, so at a transistor level, uniformly sized transistors simplify the design, and also a logic level identical gate structure can be used. Okay, and this is defined, regularity is defined by a regularity factor, which is defined as the ratio of the total number of transistor on the chip, okay, to the drawn resistor, where total resistor includes all possible ROMs and PLA transistor placement. In this table, we can see regularity factor for microprocessor chips. Here in 8080 microprocessor, the number of devices used is 4600, while its regularity factor is given by 1.1. In 8085 microprocessor you are familiar with, okay, it has number of devices is 6200 and regularity factor is given by 3.1, while in 8086 it is number of devices having 29,000, and regularity factor is given by 4.4, and Z8000 17500 5.0 regularity factor risk, you know that it is having a 44,000 devices and regularity factor has 27.5. okay, so this is the regularity factor for different microprocessor chips. So when we studied about random logic forms, so random logic form is a semiconductor design technique basically that translate high level logic descriptions directly into hardware features such as AND and OR gates. Okay, in VLSI chips, random logic is often implemented with standard cell and gate arrays. Okay, so if we define random logic, then we can say that random logic is a tag commonly used to describe digital circuits that lack regularity of circuit function, placement and interconnection of the circuit. Okay, so a particular design style of any digital logic circuit is described by random logic. Okay, so some IC circuits are placed within a layout in much the same way that small scale logic chips are placed on the wire circuit board and then interconnected. Okay, so particular types of small scale logic function may be needed at some irregular places within a circuit. So these circuit packages and their interconnection wiring sometimes appear to have randomly placed. That's why we called it a random logic form. Okay. So some advantage of it, that is efficient use of silicon area on the chip. Okay, and it is a potentially fast operation. It performs fast operation, while it has some disadvantage like lengthy integrated layout times, or second is difficulty of testing, and obviously if we modified this technique, then uh, it is costly. Okay. While if we talk about structural logic form, so it is termed used to characterize logic forms that do demonstrate regularity in their layout and interconnection. While uh, we can see in random logic is doesn't define regularity, or it defines regularity in a certain limit but not properly, while in structural logic it define demonstrate regularity in terms of their layout and interconnections. And most new digital ICs like PLA, microprogram rooms, gate arrays and standard cell are basically used structural logic forms. Okay. So in the next topic we see quasi-static register cell. Okay, so what does it mean? So in this figure we have a quasi-static binary storage cell. So first of all we have to know what is a register storage circuit. Okay, so basically we know that there are two types of storage cell that are used within a sequential digital system. Okay, so basically the application for memory cell are found within a sequential machine where the machine state must be stored. So this is basically a temporary storage, and this temporary storage is accomplished with shift registers. Okay, so basically in our syllabus there are two types of storage register cells. That is one is quasi static register cell, and another one is a static register cell. So first we can see we would see quasi static register cell. Okay, so in quasi register cell basically it is a combination of two inverter and two pass transistor, and basically non-overlapping two-phase clock. Okay, and this combination provide us a quasi-static register cell. So basically it is the same it has the same components as two-state dynamic shift register and interconnected in different way. In this diagram we can see one pass transistor called input pass transistor, and another one is called feedback transistor. Okay, and we can see clearly one pass transistor called input pass transistor control the input to the first inverter, and the second pass transistor which is called feedback transistor basically controls a feedback path from the output of the second inverter to the input of first inverter. Okay, so it is clear here when a binary value is to be stored in the register cell. Okay, when the binary value is to be stored in the register cell, whatever it is, 0 or 1, the input pass transistor is turned on. Okay, so that is because pass transistor is just pass the value whatever given in input, and it is reflect at the output. Okay, and the feedback transistor is turned off. Okay, this is accomplished through use of load signal ended with close phase phi 1. Okay, close phase phi 1 to control the gate of pass transistor, while phi 2 is low, so that the feedback path is broken at this time. In the second step, when the input pass transistor is turned on, any signal applied to D input of the register cell is passed to the gate of the first inverter, resulting in the same logic value at the output R of the second inverter. Okay, so when the input pass transistor is turned off, the value at the input node of the first inverter is stored dynamically on the parasitic capacitance of that particular node. Okay, so the value at the output, the second inverter is actively driven and logically equivalent to the stored value at the input of first inverter. Okay, then we can say that during phi 2 clock phase, uh, the output of second inverter, the output of second the output of second inverter, okay, uh, is fed back to the input of first inverter. Okay, back to fed back input of first inverter. Okay, uh, thus basically it's a logic value. As long as this feedback condition is applied, the quasi-static register cell will maintain its stored value. Okay, so this is all about for quasi-static register cell. When we talk about I-static register cell, okay, so here we have a NOR latch, basically. So fully static register cell are frequently used within a finite state machine and within a microprocessor register arrays. Okay, so one such static cell is based on classic cross-coupled set reset latch, which is a set reset latch, SR latch, containing NOR gate. Okay, and this latch uses two cross-coupled NOR gates to achieve data storage. As we know, or as we studied in digital circuit and system, this is a basically NOR latch. Okay, so what is the truth table of NOR? That is 0 0 1 1 0 1 0 1. So what is the truth table of OR? If any input goes high, then we have our output. Okay, so NOR is 1 and remainings are 0. Okay, so why we call it as latch? If we add an input that is 0 0, okay, if one input goes to 0, and here we have two output Q and Q bar, and they are complementing with each other. So this NOR latch stored 1 bit value, that is 0 or 1. Okay, and this is the equivalent circuit of NOR latch. Okay, this is cross coupled NOR latch, and this is a static register cell, obvious because the storage doesn't depend on clock signal but only on a directly coupled feedback path. Okay, so sorry. So basically in this diagram we can see NMOS static storage cell. Okay, so in NMOS static storage cell, basically this circuit is split into a cross coupled inverter pair with the set and reset pull down transistor physically separated from storage element by bus lines. These are bus lines. Okay, these are bus lines. Okay, and basically these bus holds signal representing the register cell's logic state and its complement. Okay. So if we talk about 5.3a figure, and this is a bus lines, this is the bus lines, okay, and this is a pull-up network, while this is a pull-down network. We have two output Q and Q bar. This figure is similar to previous circuit, that is NOR latch, and the only difference we can we use here bus lines. Okay, and this is a basically if we talk about figure 5.3b, completes the transformation by including pass transistors between the output of cross-covered inverter pair and the buses to set and reset pull-down transistor. Okay, so the pass transistor provide a big way to isolate the register cell from the buses. This basic static register cell consists of 6 transistors, 4 for the cross-coupled inverters and 2 that is connected to the buses. Okay, so basically we can also use a CMOS version of this cell is creating by replacing the MMOS inverters with CMOS inverters. Okay, so these are all about static register cells. Our next topic is micro-coded controllers. Okay, so what is a micro-coded controller? So basically a common method to implement complex digital system in a regular way is to use a memory-based structure, is known as micro-coded controllers. So a in this diagram we can see a micro-coded controller consists a memory unit and next address sequencer circuits. Okay, so the memory units has a micro instructions and next address sequencer directs the execution sequence of micro instructions. Okay, so micro-coded controller is a special form of any computers, while a micro instructions is a set of encoded control bits that directs the operation of logic during the clock cycle. So the execution hardware is basically a fixed, okay, as we know, and the function performed are a result of instruction placed in a micro instruction memory. So this memory is frequently we use read-only memory, and thus while it is store a micro instruction, then we call it a micro ROM. Okay, so micro-coded controller is used basically for a large machine because this control requires the overhead of next address sequence. Okay, that requires design time and integrated circuit area. While in this block we use next address sequencer. So next address sequencer is basically contains the execution sequence of micro instructions. Okay, and it simply generates we can say the next instruction address in the fixed pattern. Okay, for example by incrementing counter. So if we take down counters or up counters, then it generates a clock pulses in a sequence way or in a fixed way. Okay, so if basically status inputs are provided, the next address sequencer can modify the address of next instructions, and it depends on condition presented by the status inputs. Okay, and basically this provides a conditional branching capability. Okay, so here we can easily see we have a block diagram of micro ROM structure. Micro ROM is basically a memory which contains micro instructions, and this is basically um, a typical memory organization for a micro-coded controller consisting of micro ROM. Okay, and here we use micro ROM, which is 4096 cross 72, and a particular MAR register here. MAR register, that is memory address register. Okay, here basically memory address register has 12 address lines, and macro ROM, which are having a size is 4096 cross 72, having a 60 control lines. Okay, so this is 60 control lines, and this is 12 at next address lines, and it is total equivalent to 72 60 plus 12, that is 72-bit control word. Okay, so the memory of micro-coded controller usually had a byte data bus related to its address bus, and most of these data lines are dedicated to driving control points within a system. A few data lines are you can use to provide next address information to next address sequences, and these 12 data lines are containing the address of next instructions. Okay, the next address sequencer uses this address information along with status inputs from the controlled process to calculate the address of the next macro instructions. So almost it contains, macro ROM contains 300 kilobits, that is 2 to the power 12 into 294912, that is called 300 kilobits of controlled information, and would consumes a corresponding large basically silicon area. Okay, so this is the architecture of microprogram controlled microprocessor. Okay, so this is basically a simplified block diagram for microprogram controlled microprocessors. In this diagram, we see a memory address register, an instruction register, and program counter basically. Okay, so the micro program controller drives a data path with register, a shifter, and basically it has ALU. Okay, and we know that this is a micro row which contains a micro instructions, and this is MAR, that is memory address register, which provides an address in memory, and this is the next address sequencer. Okay, and this is an instruction register, this is program counter, ALU, shift registers, and basically registers. Okay, so this is called ALU, which perform arithmetic and logical operations. Okay, this is shift register, with shifting bit by bit, either right shift or left shift of data, and this is called register, which is store a value of data. Okay, in program counter, it's program counter incremented or decremented by 1 when it execute any instructions from memory. Okay, this is a instruction register which instruct whatever operation to be performed, and it sends a proper sequence for the next instructions to next address sequencer, and it gives also an address of memory location to MAR, memory address register, to what is the next instruction is to be performed, and it having a address of next instruction which is given to micro ROM, that is memory. So in which location the instructions should be stored. Okay, and here same operation is executed by ALU and stored in the register. Okay, and after each instructions program counter is incremented by 1. So this is all about for micro coded controllers. Okay, so if you have any doubt, then please ask me in doubt session. Thank you and have a nice day.